In order for us to be able to do our assignment, we are going to skip module 5 a bit and go to module 6 because the assignment is based on module 6. And we are doing this so that we can be able to cover all the work that requires to be covered. Once the assignment is back on, we will then go and do module 5. So here we are going to talk about illumination. So illumination is really just a fancy word that we have for lighting. It means that we are going to look at how we go about installing lights or designing lights so that we can have enough brightness in a particular area. So there are a few terms that we are going to learn, and the first one being illuminate. And basically what that means is talking to a complete unit that consists of your lamps or your light bulbs, you could call it. It consists of the parts designed to distribute your light and the parts that are there to position your lights, as well as the parts that are there to protect your lamps, and then also the parts to connect the lamps to our power supply unit. So that entire modeling or construction is called a luminaire. It's not just about the lamp, but it's everything that enables us to be able to switch on that light. Then if you see at the bottom of this page, there is a YouTube link. I want you to go and watch this YouTube, and it basically is going to explain more about the luminaire and how all of these different parts get put together. So it's a good construction, or rather a good way to start your understanding of your basics of this chapter on lighting. Then there are a few terms that we are going to talk about, and the first one really being called a candela, and it's pronounced candela as if it is candlela in isiXhosa. And basically it was the original light source that was used, the candle, and it emits your light intensity in all of your directions, and we call that a candela, the direction in which light is emitted. So this unit is used to describe the light from any light source that we now have. So originally it came from the candle, but right now any light source, be it a flashlight, be it a light bulb, we will call that unit, or rather the light from it, a candela, and the intensity of it will depend on the light source that is used. So as I've said, for example, then a torch will have a much brighter light than your candle will have, and therefore there are more candelas on a torch than you would find on a candle. And we use a symbol I to represent the candela. I've also put in another YouTube at the bottom of this slide, and that one really explains about not only the candela but also about all of the other terms I am going to go through just now. So the next thing that we are going to talk about, we are going to talk about the flow of light in air from your source. So your source could have been that light bulb, or your source could have been the candle, or your source could have been a torch, a headlamp, but wherever it is that we are getting the light from. So that flow that we have of that light is called a flux. And we use a symbol that is F to represent the flux. And we usually call this measurement that it is called a lumen. So your flux is measured in lumen, and we use F as your symbol. The measure of your total amount of visible light to our human eye from your light source is what that flux is going to be. And the higher really the lumen rating is, means that your lamp is going to be having a brighter appearance. And if you look at the bottom of the slide, I've basically put in some light bulbs on the bottom left hand side, and you can see from what we know, being your 25 or 40 or 60 watts lamps, or even if it was a 120 or 100, which I didn't actually put in the picture, but the more wattage your light bulb has got, the more lumens it has. So in other words, the more wattage you have, it means that the brighter your light is going to be. And then on your right hand side at the bottom, I've also put in other types of light bulbs that we get, where we know that we've got LEDs and your SFLs, as well as your normal lights that you have. And the difference there really is for you to determine or to see the amount of wattage that we waste. And I'll call it waste because your older version of light bulbs that we're utilizing used a lot of wattage to produce exactly the same lumen or same brightness as what we have the newer light bulbs having, and those are at a much lower wattage. So that's why even on an ESCOM side, they're always advising us that we need to go and buy your LED or your CFL lights, because they save on energy and yet they've got the same amount of brightness that your older version of light bulbs would have had. So your illuminance is really the measure of your light falling onto a surface. So from your light bulb, if you look at even at the pictures that I have there, up until your light gets to your surface point, and your surface could be your desk or whatever the place is going to be where your light is basically directing to, then that measure of the light that has fallen on the surface is called the illuminous, and it is also called your incident radiation because it's what is radiating your surface. And the symbol we use for illuminance is an E, and it is called a lux. So that measurement is called a lux. And we say that the illuminance is the total luminous flux incident on a surface per unit square. So remember we said that your flux was the flow of light from your source point on air. So that flow that then gets onto your surface on a square meter is what we call our lux or our illuminance. It is also a measure of how much incident light illuminates your surface. Then we have luminance. So before we talked about illuminance, which was the surface. Now we talk about luminance. And the luminance is really a measure of your brightness of a surface. So it's called the measure of light reflected then from the surface. So illuminance was how much light was getting onto your surface, and then luminance is how much of that light is reflected from the surface. So what do I see from the surface? That light that I see is called the luminance. And we use a symbol L for this, which we call a lumen per square meter. And with our polished surfaces, which could be glass or wood, we say that the brightness is specified in terms of our light intensity. And the luminance is called a candela per square meter. So now that we've defined the terms that we've gone through, and remember we started with our candela, which was really the power that is illuminated from our source, or the light that is going out from the source. And then we talked about the traveling of that light through air, which was our flux. and we spoke about the radiation of your surface, which was our luminance, and we talked about the reflection of the light from the surface, which was our luminance. We are now going to look at how do we go about doing calculations for our lights. And your illuminance in this case then is going to refer to the intensity of light that falls upon a surface at a certain distance d. And you can have two scenarios of this distance d. The first one being that your light source is directly above your surface point, which means it's a vertical distance d, and that is represented by E is equal to I over d squared. So d being the vertical distance from the light source to your surface, while I becomes your candela units, which talks to your illuminating power of your light source, and your E talking to your illuminance, which means that it is the incident radiation or the light falling on your surface that you are going to get. Then you also have an instance where your D is an angle from your source going towards your surface. In other words, the distance is not vertically, your surface is not directly below your source point, but it's at a certain angle where you want to know then what is that illuminance at that point. How does your source reflect or get the light to that source point? Sorry, surface point. And in this case, we utilize a formula saying IE is equal to I over d squared cos your theta. And if you look at the bottom here on your right hand side, you can see that from your source to where your point that we're wanting to know its illuminance is at, that's what the D is called. And if you can see, you have kind of a triangle there that is right angle, because from your source point going straight down up until we get to your surface, and then from the surface to that point of illuminance, you can see that we have a 90-degree angle there. So our theta we are referring to then looks at your vertical point and then at the actual distance that is away from the source point at that angle. So that's where your theta is going to be. And then having looked then at the drawing that is on my left hand side, also at the bottom, this one was really talking to when you had your E is equal to I over d squared, where you just look directly below how this would act compared to when you keep going further and further away on your direction wise, that is going to be on your right hand side. Now we're going to be looking at a few examples shown on our leaflet on module 6, which you will find on Wise Up. And the very first example is got a lamp with an intensity of 1,000 candela, and it says that this lamp is 2 meters above our laboratory bench. So your bench being the surface that we are shining upon. Then they say calculate the illuminance directly below this lamp, and therefore you are going to use the formula that says E is equal to I divided by d squared, which is 1,000 candela divided by 2 squared, and therefore giving you 250 lux. Then your second example says you are on a street and you've got a street light there that suspends a 2,000 candela light source, and it is 4 meters above the ground. Then they say determine your illuminance directly below the lamp and 3 meters to the one side of the lamp base. So here your surface is your ground point, and you first one, which is below the lamp, is simply going to be that E is equal to I over d squared, and that's going to give you the 2,000 divided by 4 squared, and you get 125 lux. Then for your second part, Because it is 3 meters on the one side of this lamp base, you basically go and draw in that triangle where you're showing the lamp source, the 4 meters above the ground, and then the 3 meters horizontally on your surface. Then you put in that dotted line, which is your hypotenuse of your right hand triangle, where you move directly from the source to the 3-meter point on the ground. And that dotted line is going to be your distance D that you are going to utilize. And in this case, because you've got a right angle triangle of a 3, 4, we should know that your hypotenuse is then going to be a 5. But if you don't know, it's simply your 4 squared plus 3 squared divide, and then you square root that, and that's going to give you 25 square rooted, which is going to be the 5. So your D is equal to 5 in this case. You then go and utilize the formula that says I cos theta over D squared. Your I being your candela you've been given, which is 2000, then your D, which is now going to be the 5, and your cos theta. Remember, cos theta is your adjacent over hypotenuse. So your adjacent to that angle on top is going to be the 4, and then your hypotenuse being the 5 that worked out. So it's going to be I over D squared times the 4 over 5 to represent the cos theta. And you get 64 lux in this case. Then we go to the third example. In the third example, we're given that we've got a discharge lamp that's suspended from the ceiling, and again it's 4 meters and it's above a bench. So our surface is a bench again, and the illuminous on the bench below the lamp was 300 lux. So your illuminous intensity of the lamp is the first one that we need to find, and then the second thing we need to find is the distance along the bench where the luminance falls to 153.6. So you've got two scenarios again, the first one being directly below the bench that we're wanting to know the luminous intensity of that lamp. And so therefore we can then utilize the formula of E is equal to I over D squared, where your D is simply the 4. So it's going to be the 300 over your 4 squared, and we get the I then becomes the 48,000 candela. Then the second part now here, they give you the Illuminous of 153.6, and we're supposed to go and find D. In other words, you have got exactly the same scenario you had in example 2, where you now need to go and draw your triangle in. So here we draw our triangle. We know that the distance from your light source to your bench is 4 meters. We don't know what the distance is from below that point up until the point where we are shining across, and we also do not have the D distance, which is our dotted line that we need to draw. So we've got two unknowns here for our distances. But what do we know? We know that we are going to have your illuminance at that point being 153.6. So what you can do is you go to your formula that is going to be E is equal to I over D squared cos theta. Now remember, what is your cos theta in this case? Your cos theta is simply your adjacent over your hypotenuse. Okay, so your hypotenuse being your D that we do not know. So therefore I can simply then rewrite that in this case and say that I've got my E being my I divide times my adjacent, which is a 4, then I divide by my D. So therefore I end up having a D cubed. In other words, then I can rewrite this formula again as what you see at the bottom there, that I now have that D cubed being equal to my 48,000 candela that you had when we were calculating your EA, and I divide that by my 153.6, and therefore I can be able to work out what my distance is if I also multiply by that adjacent. So I then get the 125, and if I cube root that, I can see that my distance was a 3. Now I just want us to take a step back again to see exactly what we did here. So the first thing is that in the first example, we had the 48,000 candela, which means we worked out what I was. That I being what your light intensity is doesn't change irregardless of your illuminous where it is in point reference to your source, but your intensity of your light is always going to be that same value. So that's why there on the d squared, when I made d squared the subject of the formula, I could say it's equal to I cos theta over my EB, which I've been given is 153.6, and I simply know that my cos theta was equal to the 4 over d. So I take that other d to the other side so that I can have a d cubed, which means I'm left with the d cubed is equal to the 4,800. That was my I that I got in A, and I divide by my 153.6, which is going to be the illuminance of where that point is going to be. I then multiply obviously by my adjacent point, and that is how I got to have the distance of 5. Okay, so your 3 that you see there was not my distance was of 5, but the 3 is the distance on the surface where the light is shining upon. So when we now talk about this illuminance and the total flux that is required at a working plane, we start looking at what we call the Lumen method. And this method determines the total number of luminaires or lights that are required to produce a certain illuminance, a certain brightness on your surface point. And this number of luminaires required is simply going to be equal to the illuminance level multiplied by your area squared, and then we say we divide by the lumens from each luminaire, and I multiply by two constants, a UF and an MF. Your UF is your utilization factor, which means that not all the light from the flux reaches your working plane. In other words, some of that light might be absorbed by your ceilings, by your doors, your walls, so it doesn't necessarily get to your surface point. And so therefore that UF can be presented by saying that is your total light reaching your working surface compared to your total light flux emitted from that lamp. And it's always a value that is less than unity, because your light emitted from the lamp is what would have been your unity value. And therefore we have got a set value of 0.9 that we utilize for our modern office buildings. Then your MF that you have in that formula represents your maintenance factor, which means that over time, when your light fittings have been installed, you will have had dust and you will have had dirt that accumulates on your fittings, and because of that dust, it basically reduces your light output of a luminaire in its life. And I think a very easy or simple example is where you have got those light covers that we usually have in our houses. And over time, you can see that you've got insects even that go and die inside there. So as they get collected between your dust and those insects and everything, your light starts becoming dimmer and dimmer until you have to take that cap off and actually go clean it up, and you can see that your room will look a bit brighter yet again. But anyway, the maintenance factor is usually given by a figure of 0.8. So we go to the next example then on your handout. And in this example, they give you a room, which is actually a workshop, and they give you the diameters of the room as a 9 by 8 by 3. So obviously the 9 by 8 is your length and your breadth, whereas the 3 meters becomes your height of this room. Then they say you've got an illuminous of 500 lux at your bench level. So at your bench level, you've got 500 lux in there. Then they say that the specification calls for luminaires having 1500 millimeters and 65 watt natural cube. Um, Having an output of 3400 lumens. Where do I see the 3400 lumens? There's a table that they put as a 9.2, and I've also inserted on the right hand side here, and you can see that for a natural light of that specification is the 3400. So if they had said it was an artificial daylight, it would have been the 2.1. If they had said it was a warm white, so you would have used whatever they had defined it as. Because they said it was natural, we take that 3400 lumens. And then they say determine the number of luminaires, which means the number of lights required for this installation. If your UF and your MF are at those constant values of 0.9 and 0.8 respectively. So you go into that formula that says the total number of luminaires is going to be the E multiplied by your area divided by the lumens from each luminaire, and then you times by the UIF times the MF, and therefore your luminaires will be required are going to be 15 because you get a 14.7, so you round it off. So now that you've got the 15 light fittings that you know you are going to spread out in this room, we need to determine how we go about installing them, like what distance from each other, or how do we go about doing the entire installation or design of installation. So here we're going to learn about what we call the spacing for the mounting of these lights and your height ratio. So it's the space between your lights compared to your height of where these lights are mounted above your surface point or your working surface, as we call it. Now, here's another thing. If you remember in the examples 2 and 3, we had a difference where one was looking at a ground level and another one was looking at a bench. All right. So we usually say that our working surface, when you are indoors, we look at a level of 0.5 above ground level. So if you are indoors and you are just told 4 meters above ground, then you always need to kind of remember that there's a 0.85 factor that you have to go and subtract, so that you always make sure we are talking about from a working surface level or a bench level, as they would name it. So they say that most of these installations are always going to be either a ratio of a 1:1 or a ratio of a 2:1. So the one being your spacing, the first part being your spacing, and the second part being your height of how these luminaires are placed. So now going back to that example, we had 15 luminaires that we had calculated would be sufficient for lighting up this area. There are just one more rule I must just tell you, and that is said that to maintain the even distribution of your lighting on your surface, we usually have the lights that are adjacent to the walls should at least be fixed at half the spacing between all of your other lights. So in other words, if your spacing between your lights are 5 meters apart, then the light that is closest to your wall will be 2.5 meters away from your wall on either side. And they say it's because in the middle of your room, you usually receive your flux from two adjacent luminaires, but at your closest points to your wall, you only receive from the one luminaire. So that's why we have that distance in there. So in our example, we know that the height we're given for the workshop was 3 meters. So if we're talking about now the height of your bench, or is going to be from your workbench to your where your light is at, is going to be the 2.15, because it's the 3 minus the 0.85 of your working bench height. And if we are assuming for this example a spacing of a 1-to-1 space to height ratio, it means that with my number of luminaires, I must now calculate on either side of the room. Remember, I had an 8 by 9. So on the side where it's 8 meters, if I take that and I divide it by my height, which is the 2.5, you can see I get about 3.7. So therefore I can say that is almost equal to 4. And if I take the side that had 9 meters and I also divide it by the 2.5, which is my height, I will see that I get about 4.1. So I can also say that means it is a 4. So this means that on either side of this room, I can have 4 luminaires. So that means I've got 4 rows and 4 columns. Looking at the bottom and how I've drawn the pictures. Then how do I know what the spacing between my luminaires is? Because now I've determined that I'm going to have 4 on each side. For my spacing between my luminaires, I simply go to my 8-meter side and I divide it by that number 4, because it then means I'm going to have 2 meters apart. So my 4 luminaires must be 2 meters apart, but I must remember the rule that says closest to the wall, it must be at half that distance. So the ones that are closer to the wall, and you should have 2 closer to your wall, are going to be at 1 meter each. So therefore I go and I plug 1, 2, 3, 4 luminaires, and then I show your 2 inner luminaires being 2 meters apart, and I go and put in 1 meter from each side of the wall, those other 2 luminaires. So you can see the side with the 8 meters I've got from the wall to 1 meter a luminaire, then 2 meters away from there another luminaire, another 2 meters another luminaire, another 2 meters another luminaire, and that last luminaire is a meter away from my wall. And you can see there it's 4 luminaires. Then I go to my 9-meter side. My 9-meter side, again, I take my 9 and I divide by the number of luminaires on that side. And so therefore I get a 2.25 meters. And the 2.25 meters becomes my spacing between my luminaires. And I must remember the ones closest to my wall, it means that I must divide that by 2, so that on either side closest to the wall, I'm going to have a 1.25 meter from that wall. And so therefore I can go, you can see on the 9-meter side, I've thrown my luminaires in, the first one being 1.12 meters away, and then the next one being 2.25, then 2.25, then 2.25, and the last one being that 1.125. And that is it, guys, from my side talking about the luminaires. Now coming is going to be your assignments for you to do some of these calculations.